Hi guys, welcome back to my system design series. If you are new to this channel or new to this playlist, then we are covering ddia book of system design. Up till now, we have completed up to chapter number 6 and we have already started chapter number 7, that is a transaction. So we will continue chapter number 7 as well in this video. This is lecture number 41 and we are covering two-phase locking versus two-phase commit, how locks prevent dirty writes, why 2PL is stricter than simple locking, shared versus exclusive locks, deadlocks, performance impact of 2PL, predicate locks and phantoms, index range locks as an approximation, and last summary. Also, please make sure you watch it 1.5x or 2x for better experience. Okay, let's get started. Two-phase locking 2PL in simple terms. Two-phase locking 2PL is a concurrency control method that makes sure database transactions happens in a safe and consistent order. It works by having each transactions acquire all the locks it needs first, that is a growing phase, and then release them, shrinking the phase. In other words, once this transaction starts letting go of locks, it can't pick up new ones. This rule ensures that the transactions don't interfere in unpredictable ways. So the database behaves that the transactions ran one after another, a serializable schedule. Okay. Now 2PL timeline. Let's discuss that. Suppose there's a transaction 1. It first acquires the lock. It is called a growing phase. Then it reaches the lock point and then releases them, which is called a shrinking phase. This ensures that no interleave, lock or unlock actions violate serializability. Okay, now let's move forward. Let's talk about two-phase lock versus two-phase commit. So it is easy to confuse 2PL with two-phase commit. It is a 2PC, but they are very different. Two-phase lock is about how a single database manages concurrency with locks, whereas 2PC, two-phase commit, is about distributed transactions agreeing on commit. So in 2PL, two-phase lock, a transactions acquire a shared or exclusive lock. Here this is for read and this is for writes. And this lock is hold until it is commit or abort. While in 2PC, two-phase commit, there is a coordinator that asks all the databases or participants to vote on committing. If all of them says yes, then it tells everyone to commit. So a typical two-phase commit sequence is the coordinator asks each node to prepare them. If all of them agree, it sends a commit. And by contrast, 2PL is about locking the data before and during the transactions to prevent conflicts. In short, 2PL is preventing conflicts inside the database and 2PC is for getting multiple databases to agree on transaction. Okay, now let's discuss how locks prevents dirty writes. Locks keep transactions from overwriting each other's uncommitted data. When suppose a transaction T1 wants to update a row, it first takes an exclusive lock on R. While T1 holds this lock, no other transaction, for example T2 or T3, can write to this row R. If T2 tries to write, it must wait until T1 finishes its commit or aborts its transaction. This means T2's second write gets delayed until T1 is done, which avoids dirty override. For example, suppose bank 1 and bank 2, both of them try to update the same account balance. The database ensures that one of the transaction gets finished, then only it allows the another transaction to write on it, so that balance is not corrupted. In short, lock force one writer to wait for the other's commit. Transactions prevent dirty writes by locking rows that will be returned to until the end of the transaction. The second write will be delayed until the first transaction is finished. That is just what we discussed. Okay. Now next is why 2PL is stricter than simple locking. Under basic locking, a program might acquire and release locks flexibility as it goes. 2PL adds strict rules on when locks can be acquired or released. Specifically in 2PL, no new locks may be taken after any lock has been released. Now, these two-phase rules mean each transaction has a clear lock point after which it only unlocks and it never locks new items. Moreover, many systems uses strict 2PL, which goes further. It holds all write exclusive locks until the transaction actually commits or aborts. Read locks may be released earlier during the shrinking phase. Releasing locks only at commit prevents any another transaction from seeing or relying on uncommitted changes. Once you start releasing the lock, you can't grab more, and usually the rights are locked up until very end. This strict discipline guarantees serializability and avoids dirty reads, but it does make concurrency more limited. Let's understand this by taking an example. Imagine two colleagues are editing the shared document. To avoid chaos, they might take turns of locking the document and then writing. For example, Alice locks the paragraph 1 to make edits, and simultaneously Bob locks paragraph 2 and writes it. But now, if Bob needs the paragraph 1, he must wait until the allies releases this lock. But they agree that suppose once someone starts releasing the lock, they won't grab any new locks on the other part of the document. And this is like 2PL. The locks here are permissions to edit, and the rule prevents consistent edits. Okay, let's make it more simpler. Suppose here is the allies. This is the paragraph 1, 2, 3, 4 and 5. When allies want to edit something, she first needs to lock all the things which she wants to edit. For example, if she wants to edit P1 and P3, she have to lock both of them. Okay, simple. And after, once she tries to release this at the same time or during this situation, you can't lock P4. That means lock everything, whatever you need, all the resources. When you are releasing, at that time you can't lock, but you have to release all the resources first and then you lock another resources. So in simple terms, if you are releasing, you can't lock. I hope this makes the whole situation very simple to understand. So let's move forward. Let's talk about shared versus exclusive lock and lock upgrades. In 2PL, two main lock types are used. First is shared lock and another is exclusive lock. Shared locks is also called locks to read. This is used when you are reading the document. This means it lets you to read the transaction but cannot let you to modify it. Many transactions can hold the shared lock on the same row at once. Suppose T1 have locked this, T2 also can lock it to read it, as they only want to read it. Now let's talk about exclusive lock. It is also called write lock. It lets one transaction to read or write a row, and no one else can touch this particular lock or row once this lock has been released. 2PL also allow lock conversation. A transaction might have started with the S lock, that is a shared lock on suppose this row, and then it upgrades to X lock if it needs to write. Upgrading from S to X is only allowed in growing phase, that is before any release. Conversely, a transaction can also downgrade from X to S during this shrinking phase if it has completed writing and only needs to read. By managing the upgrade and downgrade in the correct phase, the protocol maintains safety. And finally, with strict 2PL, all exclusive locks are held until commit or abort. This means no one sees uncommitted changes. Okay, now let's talk about deadlocks when two transactions wait on each other. That is, a deadlock happens when two transactions block each other in a cycle. Let's take an example. For example, transaction 1 tries to lock row A and then tries to lock row B as well. But simultaneously, transaction 2 tries to lock row B first and then tries to lock row A. Each of the transaction is waiting for each other to release the lock. So neither of them can proceed. In effect, both of them freeze. This is exactly when two people are blocking the doorway scenario. For example, suppose this is the door and this is a person A who is pushing the door from here, and there is a person B who is pushing the door from here. So both of them are pushing, and which keeps it as it is. So neither of them can pass on or go through this door. So deadlock occurs when two or more transactions are waiting indefinitely for one another to give up locks. The system must detect and break the cycle, usually by aborting one transaction and designing the transactions to acquire locks in a fixed order can help to avoid deadlocks. Okay, so now let's talk about performance impact of 2PL. 2PL, that is two-phase lock, ensures correctness but at the cost of concurrency and speed. Because locks are held longer, other transactions often wait. With many transactions contending for the same data, lock contention can become heavy. In practice, this means throughput can drop and response time can increase under high load. The strict rule of 2PL can reduce how many transactions can run at once, resulting in slower performance and longer wait times. In other words, the fine-grained blocking that prevents data anomalies can also make each transaction slower if it often have to queue for locks, deadlocks, and cascading rollbacks. That means if a transaction rollbacks and it forces other transaction to roll back or abort, it is called cascading rollbacks. These both are further downsides that add overhead. Okay, now let's talk about predicate locks and phantoms. A predicate locks a condition or a search predicate, not just existing rows. For example, consider a flight booking system. Suppose there is one transaction that might search for all the bookings for suppose seat 12 or between 1 to 2 p.m. A predicate lock would guard this event. That means would guard any condition that matches this particular query or condition, or even that could match this particular condition It will guard that. And this will prevent other transaction from inserting other booking for the seat 12 in that time while the first transaction is still working. In short, a predicate lock says that no new rows that satisfy my queries where condition may appear. Okay. So predicate locks are powerful. They give full serializable isolation by preventing phantoms. What is phantoms? We have already discussed, but let's do a quick revision. Phantoms is a situation where a new row appears when you perform the same query again. Okay. Now, without predicate locks, P1 might first reach row matching age greater than 30, and at the same time suppose T2 inserts a new row having the age 35. Now T1 if re-executes the query, he sees phantom, that is a new row which is added by transaction 2, and because of this predicate lock this particular row have to be weighted. But the downside is that predicate locks are very expensive to implement. The database must track arbitrary conditions and test every new insert or update against all active predicates. Database generally avoids full predicate locking because of this overhead. Okay, now let's talk about index range locks as an approximation. Okay, to prevent phantom, most systems use index range locks, which are simpler stand-in for the predicate locks. Here the idea is to use existing indexes when a transaction runs a query on index column or range. The database will lock affected index entries or gaps. For example, using the booking room example, if there is an index on room ID, the database will lock this index entry for room 123 to indicate that someone searched for room 123. Or if there is a time index, it can lock the range of time indexes, suppose 5 to 6 pm. Any future insert that would fall in this particular locked index entries will have to wait, and therefore it cannot create a phantom. So index range locking trades some precision for efficiency. It often locks a wider range than the exact predicate. It often locks the wider range than the exact predicate. But that is safe. Any write that would violate the predicate will hit the lock. So, predicate locks do not perform well. Most databases implement index range locking, which is simplified approximation of predicate locking. Here it may lock extra rows. Suppose these two rows are extra rows, but it has much lower overhead. If there is no suitable index, the database may fall back to locking the entire table. If it doesn't find the exact or relatable index, it may lock the entire table. Let's take an example and understand this. Suppose these are having customer 1, 2 and 3, having the ID suppose 1, 2 and 3, and another customer having the ID 2 wants to enter this, but this is already having a lock, so it can't enter inside this. And this is how the database prevents new unexpected rows from appearing while the transaction is still in progress. Okay, so I hope you have understood this. Let's discuss the summary. So, two-phase locking is conservative, that is pessimistic locking protocol that guarantees safe, serializable execution by splitting each transaction into a lock acquisition phase and a lock release phase. It uses shared and exclusive locks to block conflicting operations, holds lock, and thus avoids dirty writes and reads. Here, the trade-off is more blocking and potential deadlocks, which requires careful management. Then we discuss that predicate and index range locks extend 2PL to cover range queries and prevent phantom rows through true predicate locking is rarely used because of its cost. So overall, two-phase locking is a fundamental technique that keeps multi-users database correct even if it sometimes slow down the transactions. So that's it for today's video. I hope you have understood all the concepts which we have discussed in this video. If you are still watching this video, then please make sure you like this video and subscribe to my channel because that will motivate me to make more such videos. And if you have any doubts, then you can comment it out below. I will try to answer it. Apart from that, the notes of this video is in the description. Kindly please check out. Thank you so much for watching.